All right, so let's actually derive the Maclaurin series or Taylor series for some of these other functions, exponentials, sines, and cosines. So in this video, we'll focus on the exponential function. So in particular, the exponential function e to the x. And remember, if we're looking for a Maclaurin series, what that means is we're actually taking our Taylor series and centering it at x equals 0. So what that actually means in a practical sense is from our general Taylor series formula that I've listed down below, anywhere there's an a, we're really replacing that with a equals 0. So we're really writing the exponential function on the left-hand side in terms of that infinite power series representation on the right-hand side, but with the recipe for Taylor series already cooked up there. So if we insert all of those zeros, because we're doing a Maclaurin series, what we're actually looking at then is the following series. E to the x equals the function itself evaluated at 0 plus the function's derivative evaluated at 0 plus the second derivative of the function evaluated at 0 divided by 2 factorial and so on and so forth. So if we start looking at some of these quantities, well, maybe it's useful here to just make sure we're all on the same page. The function that we're talking about is the exponential function. The function that we actually want to write its Taylor series, Maclaurin series of. So all of those functions on the right-hand side here that we're taking derivatives of and all of that jazz, that's our exponential e to the x. So let's actually start cooking up some of these things. Well, f of 0, if we just evaluate our function at 0, this is just e to the 0. And well, e to the 0, that thing's just equal to 1. So that first coefficient of that Taylor series or Maclaurin series for the exponential, that is just equal to 1. Let's take a look at the next term now. F prime of 0. Well, if our function is the exponential, we take a derivative of it, that's just going to give us the exponential back. If we evaluate that derivative at 0, well, that's just e to the 0, which we already saw was 1. So the second coefficient is a 1 as well. But remember, it's really a 1 divided by n factorial, so maybe we'll put that here. So this is really 1 divided by n factorial. But then let's not forget, it's also multiplying that x. The next term of our series is, well, we get to take a look at the second derivative of the exponential. And you can probably see where this is going already. If the first derivative was equal to e to the x, well, the second derivative, when we take the derivative of e to the x is e to the x. So evaluating that second derivative then at 0, the point we're centering at, that's still again going to give us e to the 0, which is 1. So the third coefficient then, that f double prime evaluated at 0 is just equal to 1. We divide that by 2 factorial, and then we also have to remember to multiply by that x squared. And we can keep doing this for all of the terms in the series. So again, let's take a look at that third coefficient term. Again, we have the second derivative of e to the x is just e to the x. We take that third derivative, and that's going to be e to the x as well. And then probably like where you see where this is going, evaluating that third derivative at 0. So evaluating e to the x at 0 again, just gives us that 1. So the third coefficient then will be a 1 from that numerator, that f triple prime evaluated at 0, all divided by 3 factorial, and then times x squared, or x cubed, excuse me. And you might see where this is all going for the exponential. All of those derivatives evaluated at 0 are going to give us a 1. So this is actually where the exponentials Maclaurin series or Taylor series centered at 0 actually comes from. So we can reduce this to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And then if we went out more terms, we would see the next one's x fourth over 4 factorial, and so on and so forth, which if we looked for patterns, we could write this in a very compact notation from n equals 0 to infinity of x to the power n all over n factorial. And that is our Taylor series centered at 0, or Maclaurin series for the exponential function. We can do a similar thing for sines and cosines.